Okay, so let's just do a couple of examples. We're going to do the half cell or the cell potentials for these three reactions. So I have 2 silver ions plus lead solid goes to 2 silver solid plus lead 2 plus. So the first thing we need to do is we'll need to look up the cell potentials. And so we can look very quickly on here. We have silver here under my fingers, that's why I couldn't see it. Silver plus an electron, that's 0.8 volts. So I've transposed that here. This is the same reaction that we were looking at before. And now we have to go look up the lead and lead 2 plus. Now the tricky thing is you have to remember this will be written backwards. So you'll have lead 2 plus on the left and lead metal on the right hand, lead solid on the right. So we're going to scan through real quick. And here we have it. It's at minus 0. Get my mouse to show up. There we go. It's at minus, where'd it go? 0.13 volts. Now this again is written as a reduction, right? So negative 0.13 volts. Okay, so I've transposed that one as well. Now to calculate the cell potential, what we're going to do is look to see which of these two reactions needs to be flipped, right? So the lead clearly is the one that needs to be flipped. So it'll be written as Pb goes to Pb2 plus plus 2 electrons, and that's going to be positive 0.13 volts. And for the silver, we'll need to double it. Again, this is the same half reaction we dealt with before. We ended up doubling it. Like that. This is going to still be 0.80 volts. So we don't double the voltage when we double the reaction. And then we add these together. And so it's going to be 2Ag plus lead. The electrons will cancel, and then it'll be Pb2 plus 2Ag solid, right? So that voltage, when I add those together, is 0.93 volts. All I do is add these two values together, okay? Now, there's a saying, and so I like to show it this way, but there's a saying for the calculation is you just take the cathode minus the anode, but you have to be really careful when you do that. The anode minus the cathode. You have to be really careful when you do that because, like I just did, I switched the words because they're very familiar and similar sounding words, and so sometimes you flip it in your head. But you have to remember that when you're talking about flipping it, right, when you're changing the sign of this one that's down here. Now this is the cathode. If I were to subtract the anode reaction with the voltage unflipped, right, just written as it is, I would have gotten this same value. But it's really a tricky thing to keep straight sometimes. So I always prefer, right, that you just go ahead and think about like how you've done Hess's law all the way from Chem 1A. If you flip it, you change the sign, and then you just add them together. It's a much safer way to do it than trying to remember cathode minus anode, and then hoping it's not anode minus cathode, or do you flip the reaction and then subtract it, right? So there's a lot of permutations of that, and it works if you know the context. But what I've showed you here always works. There's not a context to it. It's the way these reactions work. That little cathode minus anode only works if you know why you're subtracting and what you're subtracting, okay? All right, so let's do the next one. The next one might be a little harder to find, but this is ClO2, so chlorine dioxide reacting with iodide to form chlorite ion and I2 solid. So let's go ahead and write that one down and look up the cell potentials. Okay, so this is our reaction, and so we're going to be looking for ClO2 and ClO2 minus, and then we're going to look at 2I minus and I2. Okay, so this is what we'll be looking for. All right, so where is ClO2 minus? Right, did I miss it already? Like, these are kind of hard to find sometime, right? So here's my ClO2 and ClO2 minus right here. You can see it. My mouse doesn't always show up there. That's the reaction that we're looking for there. And so I'm going to write this reaction down, and I'm going to write down its corresponding voltage, 0.95 volts. So that's what I've done here, and now you'll notice that this is going to be a stoichiometry of 2, right? So I need to keep that in mind. I'll end up doubling this. That'll be to get the electrons to cancel, but this reaction is already written as a reduction, so I'm going to keep this voltage as is, and it'll be the iodide that'll be flipping about. So that's actually what that means is, when I look it up on the table, the I2 will be on the left side of the table, and the 2I minus will be on the right side of the table. So we can sort of scan around, and I've already spotted it. It's right here. My mouse is not showing up. Hang on. There it is. So here's my I2 reduction, 0.54 volts. So let me transpose that over. So those are our two standard reductions, and what you'll notice pretty quickly is this has to be flipped, right? So I'll go ahead and flip that one. So I'm going to say 2I minus goes to I2 plus 2E minus. That's going to be negative 0.54 volts. And then the top reaction, I end up doubling it. And I need to double it to get the electrons to cancel. So I'm going to have 2ClO2 plus 2 electrons makes ClO2 minus. This voltage stays at 0.95 volts, right? We don't scale, we don't change, or we don't scale this if we double the reaction. We just leave it as it is. And so then to get the correct cell potential in the overall reaction, I'll add these two together. I'll add them up, and I'll get this top reaction that's up here. And then for the voltage, it's going to be 0.95 minus 0.54, essentially. We're just going to add these two together. And so that comes out to be 0.41 volts. And the overall reaction does add up to be this one up here. I just was lazy and didn't write it out. All right, one more to look at as practice. It's going to be this one. It's O2 plus 4H plus makes 2 zinc, or plus 2 zinc solid make H2O, 2H2O plus zinc 2 plus ion. So let's see if we can find these, right? You can see one of the half reactions will be zinc, and then you can see the other one will be the oxygen and the H2O. So let's go look for it. Let's write that out, right? And then we'll look for the reaction. So let's see, we're going to be looking for O2, right? And so I have an O2 here. This is O2 plus 2H plus 2 electrons, but this is H2O2 over here, so that's not it. Then I have a one for OH minus, so that's not it either. Oh, wait a minute. Here we go. Look at all the way at the top here. This is O2 plus 4H plus 4 electrons makes 2 H2O. So that looks like that matches pretty closely. The voltage is 1.23 volts. So there, I've transposed that one over. And, I'm leaving the states out to be expedient, but you do really need to check those. And then what we're going to do next is look for zinc and zinc 2 plus, and we need to look for that as a reduction. You'll notice this one is in the reduction form. That means this is written, zinc to zinc 2 plus is an oxidation. You can see that from the change in the oxidation state. So we need to look at zinc 2 plus on the left and zinc on the right. So we'll scan down here. And then we have it all the way down here. Zinc 2 plus 2 electrons makes zinc solid, right? And then it's minus 0.76 volts, so I'll transpose that one over. Okay, so let's take a look and see what we need to do to get this to work out. I have O2 and 4H plus 4 electrons, two H2Os, you'll notice that I have to flip this reaction, and then I also have to double it because I have 4 electrons here. So when I write it in reverse, I need to match the number of electrons. So it's going to be Zn2 plus 4 electrons, like that. Now, flipping it, I changed the voltage. I changed the sign of the voltage, so it becomes 0.76 volts. But I don't double it, right? So now I just need to add that to this reaction. I'll go ahead and write it down here. So this one's going to be O2 plus 4H plus 4 electrons makes 2H2O, like that. The electrons will cancel. That voltage is 1.23 volts. So what you see is I'll have 2 zinc on the left, that's that, O2 and 4H plus. So this side matches, and I have zinc 2 plus and 2H2O, and that matches this side of the reaction. So when I add these two together, I just have to add the resulting voltages together. And that should be, looks like 1.99 volts, if I did my math right. Okay, so that's the voltage for this electrochemical cell.